An interesting result is obtained by plotting the binding energy. Let's get the pen here. The binding energy per nucleon. So we would take the entire binding energy of the atom and divide it by how many protons and neutrons there are, and that will give you binding energy per nucleon. And we'll plot that on the y-axis, and then we'll plot the nucleon number on the x-axis. The curve will follow, but let me just talk about this here. The curve will peak at iron 56. That's what most textbooks say. New research suggests that the peak is at nickel 62. Again, that just shows how physics is continually changing as new work is done, new experiments are carried out. There's structure in the curve below that mark due to the energy levels of the different nuclei. Helium-4 has a relatively high binding energy per nucleon, and that indicates that it is very stable compared to the nucleons right about it. So again, just a reminder of binding energy. That's how much energy you have to put in to protons and neutrons to put them together to have them form a nucleus. Now, nuclear binding energies, which is what we've been talking about, are on the order of 1,000,000 times greater than electron binding energies. It's very easy to rip electrons off of atoms. We do it all the time with static electricity. However, with the nucleus, 1,000,000 times more is the energy required, and that's why nuclear reactions involve so much more energy than chemical reactions. Here's the curve of binding energy per nucleon, and that's right over here on the y-axis, average binding energy per nucleon in MeV. And here are the number of nucleons in the nucleus, atomic mass number A. And you can see how the curve goes up very sharply here, more and more energy, okay, to remove one nucleon. That's basically what it is, how much binding energy you need to kick out one nucleon, whether it's a proton or neutron. Here's the peak at helium-4. So helium-4, compared to its neighbors, has a very high binding energy because then it goes right down here. That means helium-4 is very, very stable. The curve keeps rising right up to around the iron-nickel area right here, and then it decreases. And on the next slide, we're going to talk about what it means for the binding energy for nucleon to be rising up until it gets to this point, and then it steadily decreases the more massive elements we talk about. The significance of the binding energy per nucleon curve, remember, it kind of rose like this. I'm leaving out helium, and then it started going down right after nickel, around nickel area, iron, etc. And helium peaked here and then came down. Elements to the left, okay, to the left of iron 56, are created in stars using a fusion reaction. More about that later. But basically, you have nuclei are combining to form a larger nucleus, starting by combining hydrogens into helium, which is the main reaction our sun uses to release energy, and that will release the binding energy. So that's fusion. So to the left of that line, you have fusion reactions. These reactions release more energy than is put into the reaction, and that's what causes our sun to shine. Elements to the right are created in the last stages of a star exploding, or supernova. That's because they release less energy than the energy required to fuse smaller nuclei. And the only way you can get enough energy to put these elements together, to the right of nickel, to the right of iron 56, is by a supernova explosion. So the heavier elements all came from stars exploding. The lighter elements were created as a star was going through its life cycle. Although the heavier you get, the closer you get to iron, a lot of those elements were formed just in the first few seconds of the supernova explosion.